Imagine a world where rings of ice and rock stretch across the sky like a cosmic bridge, where geysers shoot hundreds of kilometers into space, and where one moon hides an ocean that could harbor life while another moon is covered in liquid methane lakes. This isn't science fiction. This is Saturn's family of moons, and they might just be humanity's next home. While Saturn itself is a beautiful but deadly gas giant, its collection of over 80 moons presents some of the most intriguing possibilities for human colonization in our entire solar system. But could we actually survive there? Let's find out. Saturn sits almost 10 times farther from the Sun than Earth does, at an average distance of 1.4 billion kilometers. This means it receives only about 1% of the sunlight we get on Earth. The journey to Saturn takes between 6 and 7 years with current technology, making it one of the most remote destinations humans have ever considered for colonization. Yet despite these challenges, Saturn's moons offer resources, energy, and scientific opportunities that might make the journey worthwhile. Let's start with Titan, the second largest moon in our solar system, and arguably the most Earth-like world we've ever discovered. Titan is larger than the planet Mercury and is the only moon with a thick atmosphere. In fact, Titan's atmosphere is denser than Earth's, with a surface pressure about 1.5 times what we experience at sea level. This is huge for colonization because it means you wouldn't need a pressure suit, just a warm coat and an oxygen mask. The atmosphere is mostly nitrogen, just like Earth's, with about 5% methane. The surface temperature on Titan averages negative 179 degrees Celsius, cold enough that water ice is as hard as rock and methane exists as a liquid. Titan has weather, clouds, rain, rivers, lakes, and seas. But instead of water, these are all made of liquid methane and ethane. The largest seas on Titan are in the polar regions, with Kraken Mare being bigger than the Caspian Sea on Earth. What makes Titan extraordinary for potential colonization is that dense atmosphere. It provides protection from radiation and micrometeoroids, things that are major threats on airless moons. You could theoretically walk on Titan's surface with just an insulated suit and breathing apparatus, without the bulky pressure suits needed on our moon or Mars. The low gravity, about 14% of Earth's, combined with the thick atmosphere, means humans could actually fly on Titan with just wing attachments. Imagine that, actual human-powered flight on an alien world. But the cold is a serious challenge. Everything we use on Earth becomes brittle and breaks at Titan's temperatures. Metals become fragile, plastics shatter, and rubber turns to powder. Any colony would need to use specially designed materials and maintain heated habitats. The good news is that Titan has abundant energy resources. The moon is covered in hydrocarbons, essentially natural gas and oil scattered across the surface. These could be harvested and burned in oxygen brought from Earth or extracted from water ice, providing heat and power. Titan also has water ice beneath its surface. Radar data from the Cassini mission suggests there's a subsurface ocean of liquid water and ammonia about 50 to 80 kilometers below the surface. This ocean might be hundreds of kilometers deep. The presence of both surface hydrocarbons and subsurface water makes Titan incredibly resource-rich. A colony could potentially manufacture everything it needs locally, from plastics to rocket fuel. The scientific value of Titan cannot be overstated. The moon has organic chemistry happening on a planetary scale. The atmosphere contains complex organic molecules, the building blocks of life. While it's too cold for life as we know it on the surface, that subsurface ocean could potentially harbor life. Even if it doesn't, studying Titan's chemistry gives us a window into what early Earth might have been like before life arose. Now let's talk about Enceladus, a small moon only about 500 kilometers in diameter, but it might be the most likely place in our solar system to find alien life right now. Enceladus has a smooth, bright surface covered in fresh ice, making it one of the most reflective objects in the solar system. But the real action happens at the South Pole, where enormous geysers shoot plumes of water vapor, ice particles, and organic molecules hundreds of kilometers into space. These geysers come from a global subsurface ocean that lies beneath an ice shell about 20 to 30 kilometers thick. The water in these plumes contains salt, organic compounds, and molecular hydrogen, which is a sign of hydrothermal activity on the ocean floor. This is exactly the kind of environment where life thrives on Earth, around deep-sea hydrothermal vents. The ocean on Enceladus is kept liquid by tidal heating, the same process that keeps Europa's ocean liquid. Saturn's gravity stretches and squeezes Enceladus as it orbits, generating internal heat. For colonization, Enceladus presents interesting possibilities. The geysers provide easy access to water without having to drill through kilometers of ice. A colony could literally collect water falling from the sky. The subsurface ocean could be accessed through existing cracks and fissures at the South Pole. Building a habitat beneath the ice would provide radiation protection and access to liquid water. However, Enceladus is tiny. Its gravity is only about 1% of Earth's, barely enough to hold you down. This creates health problems for long-term habitation. The moon also has no atmosphere, so surface operations would require full pressure suits. But the biggest draw of Enceladus is astrobiology. If we find life in that subsurface ocean, it would be one of the most important discoveries in human history. A research colony on Enceladus would be primarily scientific, studying that ocean and searching for life. Moving on to Rhea, Saturn's second largest moon. Rhea is about 1,500 kilometers in diameter, heavily cratered, and composed mostly of water ice with a rocky core. What makes Rhea interesting is its stability and relatively lower radiation environment compared to some of Saturn's other moons. Rhea orbits outside Saturn's main radiation belts, making it safer for human habitation. Rhea has a very thin atmosphere of oxygen and carbon dioxide, though it's far too thin to breathe or provide any real protection. The surface is ancient and geologically dead, similar to our moon. Surface temperatures average around -174 degrees Celsius. While Rhea doesn't have the exciting features of Titan or Enceladus, it offers something equally valuable for colonization: stability and resources. The moon has abundant water ice that could be mined for life support and fuel production. The lower radiation levels mean less shielding is required for habitats. Rhea could serve as a stable base for resource extraction and as a way station for missions to other Saturn moons. It's predictable, which is actually a valuable trait when you're trying to keep humans alive millions of kilometers from Earth. Then there's Iapetus, one of the strangest moons in the solar system. Iapetus has a two-toned appearance, with one hemisphere being extremely dark and the other extremely bright. It also has a massive equatorial ridge that runs around most of its circumference, making it look like a walnut. This ridge includes some of the tallest mountains in the solar system, reaching 20 kilometers high. Iapetus is far from Saturn, orbiting at about 3.5 million kilometers, which means it experiences much less radiation than inner moons. The surface gravity is only about 2% of Earth's. While Iapetus probably isn't a primary candidate for colonization, its unique features make it valuable for scientific research, and its distance from Saturn's radiation makes it relatively safer for long-duration missions. Let's discuss Dione and Tethys, two mid-sized moons that orbit within Saturn's radiation belts. Both are composed primarily of water ice and have heavily cratered surfaces. Dione shows evidence of past geological activity, with wispy terrain and possible past cryovolcanism. Tethys has a massive impact crater called Odysseus that's 400 kilometers across, nearly 2/5 the diameter of the entire moon. Recent data suggests Dione might also have a subsurface ocean, though this is less certain than for Enceladus or Titan. Both moons have water ice resources and could potentially support small research outposts, though the radiation environment makes them more challenging than outer moons like Titan or Rhea.